In 2026, an engineer stood under a 345 kilovolt grid line, its power lethal on contact. 18 months later, that same power runs a chip at 1 volt. The full drop happens in stages inside one campus. Here's the scale. A single AI training campus can now pull 100 to over 1,000 megawatts, the appetite of a small city. Getting that power in, stepped down safely, and delivered clean to the chips is the hidden hard problem behind AI. Any stage fails, every rack goes dark. So how does a wall of grid voltage become 1 gentle volt? Start at the top. The grid ships power to the campus at very high voltage, 345 kilovolts, sometimes 500 kilovolts or even 765 kilovolts. Why so high? Here's the trick that makes long-distance power possible. Electricity loses energy as heat when it fights its way through wires, and that loss grows with the current, the amount of electricity flowing. Push the same power at higher voltage and the current drops. Lower current means far less heat wasted in the line. This is why we don't just send low voltage down 100 miles of cable. It would bleed away as warmth before it arrived. So the grid does the opposite. It cranks voltage way up, keeps current low, and coasts the power across the countryside cheaply. That high voltage flow rides the big steel towers you've seen along highways, humming above the fields. At the edge of the data center campus, it finally arrives at the utilities transmission substation, the first gate. Think of it as the loading dock where raw grid power pulls in. Nothing here is safe to touch. A single 345 kilovolt line carries enough to vaporize metal. But raw grid voltage is useless to a chip. It has to come down. And that raises the next question. How do you drop a number that big? Now the first big drop. Inside the substation sit giant step-down transformers, each the size of a small house. Their job is to take 345 kilovolts and bring it down to a medium voltage, somewhere in the 13.8 to 34.5 kilovolt range for the campus. So what is a transformer actually doing? 2 coils of wire share an iron core. Power flows into the first coil and out of the second, and the ratio of turns between them trades voltage for current. Fewer turns on the way out means lower voltage, and in exchange more current. No moving parts, no engine, just wire and iron, and the physics of a changing magnetic field. That's why transformers hum but never spin. Here's the part operators lose sleep over. You can't run a city's worth of power through one box and hope. A single fault could black out the whole site. So substations use switchgear and breakers, heavy switches that snap a faulty line dead in milliseconds, plus redundancy. Engineers call the spare capacity rule N+1. Always one more unit than you strictly need, so one failure never stops the flow. Medium voltage now leaves the substation, fanning out across the campus. But it's still thousands of volts too high for a building. Follow the power into the buildings. Medium voltage runs across the campus to smaller unit substations tucked beside each data hall. There it stepped down again to 480 volts 3-phase, the workhorse level that feeds the building's floor. But here's a problem the grid can't solve. The grid dips, sags, and sometimes fails outright. A chip mid-calculation can't wait for the lights to come back. So this floor is where the safety net lives. Big battery systems, the UPS and uninterruptible power supply, sit inline holding a charge. If the grid so much as flickers, the batteries carry the load instantly, without a single missed beat. That buys seconds. And in those seconds, backup generators roar to life to carry the site through a longer outage. It's like paying 2 extra electric bills just to guarantee the first one never drops. From there, power distribution units, the PDUs, fan the electricity out to the rows. They split 480 volts down to 208, and route it, breaker by breaker, to the racks standing in long cold aisles. Now the power is finally at the doorstep of the machines. But a computer chip doesn't run on 208 volts. It runs on roughly 1. So there's one more descent to go. Open the rack. This is the last mile, measured in millimeters. Power arrives at the rack as 208 or 240 volt alternating current. Right there, power supplies convert it to direct current and drop it onto a metal busbar, a thick copper spine running up the rack, at 12 volts or in newer designs 48. That direct current rides the busbar straight to the boards. And on each board sit small converters called voltage regulator modules, sitting inches from the silicon. Their job is the final plunge. From 12 or 48 volts down to the roughly 1 volt, the GPU core actually demands. Why so low and why so close? Here's the number that forces the design. A single modern AI chip can pull hundreds of amps, over 1,000, all at about 1 volt. That's a fire hose of current through a whisper of voltage. And current turns wire into a heater. The farther it travels, the more it wastes. So the last conversion has to happen millimeters from the chip, or the power would cook itself before it arrived. That's why these converters crowd the silicon like pit crew around a car. One campus, 5 voltage steps, and it all ends here. 1,000 amps whispering into a single volt. Which raises one last question. Where does all this power even come from now? Now the twist reshaping the whole industry. For a century, you built near the grid and drew what you needed. AI broke that habit. Here's the bottleneck. When a company wants to plug a giant new campus into the grid, it joins an interconnection queue, a waiting line for a grid connection. That line can run 3 to 7 years. But an AI company wants power in months, not years. Speed to power is now the whole game. So instead of waiting, they're building their own power plants on site. Gas turbines the size of jet engines. Banks of fuel cells that make electricity from natural gas or hydrogen through a chemical reaction, no combustion. And in the boldest deals, operators are signing up for nuclear, including small modular reactors, compact next-generation plants meant to sit right beside the campus. On-site power isn't only about speed. It's about the shape of the demand. An AI cluster runs flat out, 24 hours a day, 7 days a week. A constant, heavy pull the old grid was never designed to feed. Building your own generation lets you size it exactly for that relentless load and keep the racks fed even when the grid stumbles. The plug, in other words, is moving onto the property. So step back and watch the whole chain at once. Here's the whole descent in one breath. It starts at 345 kilovolts on the grid line, enough to leap through the air and kill. The substation transformers drop it to 13.8 kilovolts for the campus. Unit substations bring that to 480 volts for the building, with batteries and generators standing guard behind it. Power supplies in the rack turn it into 12 or 48-volt direct current on the busbar. And the little regulators, millimeters from the chip, make the final plunge to about 1 volt. 5 stages. Each one trades voltage for current or slams a fault shut before it spreads. That's the answer to the paradox we started with. Powering AI was never one giant plug in the wall. It's a 5-stage staircase from a lethal grid line down to a single gentle volt. And because that staircase can't be built fast enough, the industry is now hauling the power plant itself onto the campus to feed the climb. But all that power turns into heat, 1,000 watts pouring off a chip the size of a stamp. Next, we open the box on how these campuses haul that heat away, and what it costs in water and energy to keep the silicon cold. Subscribe and we'll take you inside the cooling loop.